So now that we have seen how we will construct a machine learning model for materials, let us see how we can start interrogating the model and then start deciphering how the model is making the type of decisions that it is making. So for this, we will look at a couple of examples. The first example is going to be looking mainly at the prediction of yield strength for different types of multi-principal element alloys, which are otherwise also known as high entropy alloys. And this is a paper which has been written by Kyung-Tae Lee and Prasanna Balachandran. And then the second example is something that we will pick up from the work that has been done in my own research group, where we try and understand what are the origins of hardness of different types of high entropy alloys. In the first case, the machine learning process comprising of an ensemble of support vector regression, and in the second case, the machine learning process comprises of an ensemble of neural networks. So they are both somewhat related in the sense that one is looking at mechanical property like yield strength, and then the other is looking at also at a mechanical property like hardness, and both of them are for high entropy alloys. So in that sense, there are some underlying similarities, and it will be useful for us to see how the two different approaches have been taken for these two different types of problems. So let us start with the first example, which is basically the paper by Kyung-Tae Lee and Prasanna Balachandran. So here they are trying to predict the yield strength of different alloys, and then at the same time they are also trying to ensure that they get some of these values as a function of the testing temperature, meaning that they have looked at the tensile test not just at the room temperature but also as a function of different temperatures. So the problem statement for this is given over here. They want a model to predict the yield strength of the as-cast MPAs, and then after predicting the yield strength, they want to explain the trends in prediction using XAI algorithm. So XAI stands for explainable artificial intelligence. So in this particular case, they have relied on SHAP analysis. They've also relied on something known as CP plots. We are not going to discuss that too much. We have discussed the basis of SHAP analysis, but we have not talked about the CP plots. So we are going to leave that out and focus only on the SHAP analysis that has been done. And by doing that, the authors hope to reveal a suitable design criteria for making high strength, high entropy alloys, and they want to have this criteria as a function of temperature. So as we said, before you start your machine learning process, you need to have a data set. So after cleaning up their data sets, they had a total of 353 data points. By the way, this is one paper where they explain how they are doing the data pre-processing quite clearly, and so I would urge you to look into this paper and see how this pre-processing can be done. Initially, they started out with 36 input features, and they looked at these features using this composition-based feature vector type of approach, where they were using the MACY package. So when we were discussing about the composition-based feature vector, we had also discussed something about the different feature addition schemes, like MACY was one of them. Once they have the data set and the features, they use the support vector regression in order to train the model. And then in order to refine it, they use a grid search for tuning the hyperparameters of the model. So this is an overview of the work that they have done in terms of the problem statements, as well as how they have proceeded with doing the machine learning. So while we will be focusing more on the SHAP, I am also going to highlight as we go along the way how the machine learning was done as well. So the first thing over here, after the data set was pre-processed and everything, is to do some amount of feature engineering. Like I said, they started with a total of 36 inputs initially, but eventually their final model had a total of 11 inputs. So what you basically do while you are doing feature engineering is go ahead and plot this PCC matrix, or the Pearson correlation matrix. And so when you are looking at this Pearson correlation matrix, you can start looking at the correlation between different features. So obviously, if you go along the direction, that is a correlation of the feature with itself. So that's always going to be 1. But then you start looking at the correlation for the other pairs of features. So for example, if you are looking at NComp and then you are looking at test temp, you will see that there is hardly any correlation, which makes sense because you can take any composition and you can test that at any temperature, right? So if you want to understand the correlations for this particular problems a little bit better, I would urge you to pause the video. For your reference, the authors have already added the description of each of this notation. So they are looking at NP valence, mean NP valence, and mean NP valence here is the average number of p valence electrons. So in other problems that we were talking about, we were continuously discussing valence electron configuration. Here the authors have chosen to look at the electronic structure from a slightly different perspective. So they are looking at number of average filled p shell valence electrons as well as the number of average filled s shell valence electrons. They have also used the standard deviation of the electronegativity values for each of the alloy compositions. They're also looking into the number of unfilled d orbitals and so on. NComp gives you the number of constituent elements in the high entropy alloy composition. Since they are looking at the yield strength as a function of temperature, the melting temperature of the alloy is also important. Now, melting temperature is typically not something you will find very clearly in the dataset, and therefore what they have done is they have simply looked at a mean melting temperature, which is a composition based average of the melting temperature of the individual elements, and so on and so forth. Now, after the feature engineering is done, the next thing I would want to do is show the overall snapshot of the workflow. So you can think of their work as having 4 major steps. The first step, once you have your features ready and once you have your data set ready, is to actually go ahead and do the machine learning part, which they have done with support vector regression. And they have not just used a single support vector regression, they have actually used a large number of support vector regression, about 30 of them, and then they have looked at this entire ensemble. Again, I just want to point out this is aligned with some of the discussions we have had earlier in this course, that when you are working with sparse data, using this ensemble based methods can always be useful. So that just ensures that the number of variables that are getting involved, if those number of variables are fairly large and then the number of data points is fairly small, there is a good chance that you will be overfitting. So when you use this ensemble type of methods, you have a chance that you can reduce that type of overfitting. So after the first step, which is actually doing the yield strength prediction with the support vector regression, let us move on to the second step. And here they have done the SHAP analysis, which predicts the feature contribution. Now, one thing I just want to mention is the type of SHAP analysis being done over here is what we would classify as a local SHAP analysis. So once the SHAP analysis is done, they have now tried to take it to the next level. And what they have done is use the SHAP values in order to perform this k-means clustering. So basically you do the SHAP analysis for all of the features, and then after that you use those values in order to do this k-means clustering. And what they are finding out is different clusters of high entropy compositions which are similar. So the compositions within the cluster are similar in terms of the SHAP values. So they have eventually found out 4 different clusters, and then each of these clusters are similar in terms of the constituent compositions within the cluster. So once the k-means clustering was done for each of the cluster, they have again done a SHAP analysis. But here, unlike in step 2, they are looking at the global SHAP values in order to extract the overall trends in the feature contribution within the cluster. And the reason they have done this is they found out that within each cluster, the feature seems to be contributing differently. So you then set up a computational pipeline where you find out similar compositions by looking at your local SHAP values, and then within those similar compositions, you will then perform a global SHAP analysis in order to understand how the features are acting up within those cluster of compositions. So just to give you a snapshot of the support vector and the k-means results, The figure on the left is a parity plot that shows the comparison of the predicted and the experimental yield strength, and as you can see, most of the composition are fairly close to the parity plot, even though you do have a decent amount of mean absolute error. It is not surprising for problems of this kind because you can actually have quite a bit of scatter in the experimental data as well. But then the point over here is the support vector regression that they developed was quite capable of predicting the yield strength value with a reasonable level of accuracy. In fact, if I remember correctly, they reported a R-square of about 0.82 for this particular model. After this, upon performing the local SHAP analysis, they came up with 4 different clusters of compositions, and the further analysis in order to explain how different features were working was done for individual clusters separately. So after this clustering was done, the global SHAP analysis was then performed, and then over here you can see how the SHAP values change with the features and how the features are contributing towards the prediction of the yield strength. What I want you to note is if you look at this different SHAP plots, you will see that the feature contributions are actually markedly different. So for instance, in your first cluster, most of the features seems to be having a positive contribution. In the second cluster, most of the features seem to have a negative contribution, with some of them having strongly positive contributions, and so on and so forth. So as you can see, for this third cluster also, it is markedly different from the other two, and then the fourth cluster is also quite unique. So this was actually a very smart move by the researchers to do the analysis in this form, because they could now start identifying different classes of composition where the features were acting differently. Now, if you look at this figure on the right, if you look at the compositions of the different classes, what the authors have done is they have simply made pie charts which shows how many times a particular element was occurring in that cluster. So if you look at this pie charts, you can see that in cluster 1 it was mainly a chromium, iron, nickel, aluminum type of alloy system. In cluster 2 it was a nickel, iron, chrome, cobalt type of alloy system. So what you basically notice is you had a lot of aluminum in there as a percentage, whereas in the second cluster you now had cobalt. So aluminum over here was FCC, it has a certain number of valence electron concentration. Cobalt, the value is different and the crystal structure is also different. As you come to the third cluster, now once again you see that the chromium and nickel is less. So this is basically a titanium, aluminum, niobium, iron, nickel type of alloy. The amount of chromium is now quite less. And in the fourth cluster, it basically becomes a niobium, molybdenum, titanium, hafnium type of alloy. So the fourth cluster is essentially more like what we would call the refractory high entropy alloys, whereas in the first cluster, it is really the non-refractory transition metal type of high entropy alloys that seems to be the baseline material. So clearly, one would expect, given the refractory and the non-refractory nature, that cluster 1 and cluster 2 would be extremely different. And then if you look at the SHAP contributions in case of the cluster 1 and cluster 2, you will see that this is quite different. Even this value, this mean value about which the SHAP has plotted, has also changed quite a bit. So in one case, you will see that most of the contributions are positive. In the other case, you will see that you have a large spread of the feature contributions. So let us just take up one of these clusters and look at its SHAP analysis to understand what's really happening. So this first cluster is basically where you have got the chromium, iron, nickel, aluminum type of high entropy alloy. Not all of them obviously would be a chromium, iron, nickel, aluminum, but basically what I mean is chromium, iron, nickel and aluminum occurs with a much higher, and titanium as well, occurs with a much higher frequency in the alloys falling in this cluster than any of the other elements. So what you see over here is there is a very strong positive contribution for the test temperature, you will see that when the mixing entropy is concerned, this thing is actually getting spread over quite a bit. The NComp mostly seems to have a positive contribution. If you remember, NComp was basically the number of elements in that particular composition, and as the number of elements are increasing, the entropy is increasing, and as the entropy increases, the high temperature structure gets stabilized, and therefore when you are looking at the high temperature yield strength, one can understand that there will be a positive contribution. So similarly, you will see that the melting temperature and all, they also have a positive contribution towards the yield strength. So from here, if you now want to see which feature is actually having the maximum positive contribution, you can start identifying that. If you can also then look at which feature has the maximum negative contribution. So all of that information is something that you will extract from this cluster. Now, what would have happened if you had done this type of analysis without dividing the alloys into cluster? You would be seeing a much larger spread. In fact, if you go back to the previous figure, you will see that if you are trying to combine these shaft plots by looking at all of the alloys together, you will be having a lot more spread in the shaft values of the features, and it would be very difficult to really isolate the feature contributions because the features seems to be contributing differently in different clusters. Now, one of the things I want to emphasize for this particular example is that we have been using this composition based feature vectors, but we have ignored the microstructures. Now, yield strength is something which is a very strong function of the microstructure of the material, and this becomes especially important if you are comparing fine grained and coarse grained materials. So what the authors did in this particular case was to work only with arc melted type of samples, as cast samples, where the grain sizes are going to be fairly large, and therefore this Hall patch type of strengthening is not going to be quite as significant. And that allowed them to treat this as a composition based feature vector type of model. The next example that we are going to talk about also has this underlying assumption that the data set is created mainly from this as cast type of materials with similar types of grain structures, and that is the basic assumption with which the microstructure has been ignored while developing the model. So for this second example, we are trying to find out the physical origins of hardness in different types of high entropy alloys. And here the problem statement is shown over here. We want to predict the hardness not just for discrete compositions, but we want to be able to predict them along continuous composition pathways. And then these predictions will have to be validated, whether it is with a test data set or with experiments. And then after that, the interrogation part of the model really deals with how the composition tuning alters the hardness, how the features assume importance locally. So the overall workflow for this particular example is shown on the right. You first start out with your high entropy alloy database, and to that you combine your alloy features, which is something that we have discussed quite a bit. After that, you want to make the neural network ensemble. Essentially, since it's an ensemble of large number of neural networks, you have to do some average pooling, and so from there you now have a model which will give you the hardness of high entropy alloys. Once the model is ready, now you can write a script for creating an array of inputs along a certain composition pathways, and then the output from there is going to help you get the hardness distribution. So once you run the model, once you have your outputs, after that the next part is to do the model interrogation, which is done by probing continuous compositional pathways, looking at the local partial dependencies. So this is basically the Cosmo type of thing that we were discussing in our last lecture. And then after that you have got the other supplementary methods that were used, which comes primarily by way of doing experiments as well as by performing DFT calculations. So we are not really going to talk too much about the experiments and the DFT calculations over here. We will focus on how the machine learning model was set up, and then after that we are going to focus on how you are doing the model interrogation in order to extract the physical origins of hardness. So the overall process is like this. You have your starting alloy and you need to find a proper uh, representation for the alloy. So in this particular example, I'm looking at aluminum, cobalt, chromium, iron, nickel alloy, and then the target property is there in the data set, which happens to be in this case 510 Vickers hardness. The alloy has to be represented in a proper manner, and so that comes by representing it using its composition. So this is a equiatomic high entropy alloy. All of those elements will have a composition of 0.2. Once you have the compositions ready, then you need to add in the descriptors, or basically what we call the features. So here we have used three classes of features: thermodynamic features. So that would be things like chemical enthalpy, elastic enthalpy from a shell-based model, configuration entropy, and so on. Then we have added the asymmetry features. So that would be things like the metallic radius, asymmetry in metallic radius, asymmetry in covalent radius, asymmetry of molar volume, and so on and so forth. And then we have added a number of composition average features such as the valence electron concentration and the density. So once your problem is featurized, you will have to input all of those features into a neural network. After you develop the neural network model, you want to cross-validate it heavily. So 5-fold cross-validation was done, and most of the time you can see that the predictions fall within a 20% error. And the overall R-square value in this case was coming out as 0.85. So when you do the cross-validation, you will have to look at the R-square value in each fold of the cross-validation, and you need to ensure that those values are not changing quite significantly. Once that is done, you know that you have a reasonably good cross-validated model. So after developing the cross-validated model, it was then used on a completely new data set, which is basically the testing data set, which had about 58 alloys. And when the predictions were made for the testing data set, it turned out that the R-square value was about 0.81 or so in this case. So this was fairly comparable with the training data fit. And then the testing data actually had a number of points, those red points shown over here, which were not arc melted samples, rather these were samples that were made by spark plasma sintering. Now what happens when you use spark plasma sintering? You will typically end up with finer grained material, and therefore the hardness values are also going to change quite a bit. So it's no surprise that most of the compositions, there are of course some exceptions, but most of the compositions which the model doesn't get correctly happen to be the one which are made using mechanical alloying and spark plasma sintering, which results in nanocrystalline high entropy alloys. So this is one of the reasons why I was emphasizing quite a bit that you need to ensure that you know your database well enough, you explore your database well enough. So clearly these type of red dots should not have been included, because the model that was trained was anyway not going to predict that properly. The good thing though, of course, is we had put this in the testing data set just to see how well the model works. We had deliberately excluded them from the training data set. One of the goals of this model was to predict the hardness variation along continuous composition pathways. So in this case, one of the pathways that we established was by continuous addition of aluminum. Now this is a quinary system, meaning that there are 5 different elements, and I am representing this for easier visualization by using a ternary type of diagram. So what that basically means is one of the vertices would have to represent a ternary, whereas the other 2 vertices are representing elements, pure elements. The way in which this representation is done is basically dependent on the experimental values with which we are going to do the validation. Since the experimental values were measured by varying aluminum and titanium, the pseudo-ternary plot shown over here has aluminum as one of the vertex, titanium as one of the vertex, and then the chromium, iron, nickel, whose ratios were not varied in the experiments, as another of the vertex. So what you can see from this figure is that as you are adding aluminum, this is leading to a sudden increase in the predicted hardness. And this jump is quite apparent in this region when you are going from only a 7% to a 10% aluminum. In other words, you actually see a markedly nonlinear jump in the hardness value over here. If you add titanium, this also results in considerably higher peak hardness. Now, you don't have such a huge jump at any one composition step, but overall you can see that you are going from about 400 levels of Vickers hardness to well in excess of 700 level Vickers hardness. So both aluminum and titanium seem to increase the hardness in this particular alloy. Aluminum seems to do that at a certain uh, composition range between 7 and 10%, and then after that the increase is not quite as marked, whereas in case of titanium the increase is quite gradual, even though it is leading to higher values of hardness. So one of the things you can figure out is the reason for this jump quite likely is going to be a change in the crystal structure, possibly from a FCC type of phase to a BCC type of phase, because that results in going from a high number of slip system to a low number of slip system. And when you match with the experiments, you will see this is actually exactly the composition where aluminum addition results in this phase transformation. So one can then, compare this hardness variation along composition pathways with the experimental results, not only of hardness but also the X-ray results, which gives you the phases that are present, and get the physical insight as to why you had this nonlinear jump in hardness. Similarly, the same type of work was done for aluminum, titanium, chrome, iron, nickel alloy. And here, when you are looking at the experimental data, you will see that the experimental data is varying in a slightly different way. So you are going from aluminum content of 0 to aluminum content of about 7%, and then you essentially go to this point. So the composition pathway reported in the experiments is something of this nature. So when we do the hardness predictions, we will see that the trends between the actual hardness and the predicted hardness seems to match pretty well. And here, furthermore, we had done the DFT calculations to calculate the formation enthalpy of the body-centered cubic phase. And you will see that as we are increasing the aluminum content, the formation enthalpy drops, and then this trend in formation enthalpy is almost opposite to the trend in hardness. So now you know that the formation of the BCC is really driving the changes in hardness, and this is how you can actually use supplementary computational methods in order to extract insights from your machine learning model. In addition to that, when we try to decode the decision-making process, we will be using the COSMOR framework, which we had just discussed in the previous lecture. And so here, for the COSMOR analysis, what we are doing is we are simply looking at the change in the composition. So that is the compositional stimulus that we are providing to the machine learning model. And then we are looking at the feature contribution in terms of the contribution to the overall hardness. So this was done for the variation of lot of different elements, but let us pick only one and study that in much greater detail. So for that, let us look at this aluminum, titanium, zirconium, hafnium alloy. And so here the titanium, zirconium, hafnium ratios are not being varied, and only the aluminum content is being varied. And so along the x-axis, you have an increase in the aluminum concentration. The black curve over here, that gives you the overall hardness. And this point over here is what we would call a baseline hardness value, because this is where the aluminum concentration is 0. After that, by adding aluminum, the hardness is increasing. We are simply moving away and higher up from the baseline value. So when you plot out this partial dependencies, you will see that the delta H chemical, the formation enthalpy, which was computed using Miedema's model, that seems to have a much higher contribution to the overall hardness. Now, as we had already discussed, when we are doing an analysis like this, it is probably not enough to simply look at how the feature is affecting the hardness in an absolute sense, but it would also make sense to look at how the value of the feature itself, not just the contribution of the feature to hardness, but how the value of the feature itself is varying. So if you look at that, this is case D, and case D is represented by the blue lines over here. So the blue line over here for the delta H elastic stays more or less constant. In other words, the elastic enthalpy is really not playing up too much, and you can also see that the elastic enthalpy doesn't make much of a contribution. It doesn't even show up. Then if you look at the delta H chem, you can see that the value of the chemical enthalpy decreases sharply, and then this is basically something which is playing up in terms of increasing the hardness values. So the chemical enthalpy decreasing means now the bonds that are being formed are getting stronger and stronger. This is something that people have also seen with the addition of aluminum to different high entropy alloys. It tends to promote a more ordered structure, which indicates stronger bonding taking place. And so as the bonds are stronger, breaking those bonds to create plastic deformation required is also going to become more and more difficult, and this delta H chemical is therefore adding quite significantly to the hardness of the alloy. If you look in terms of the anisotropy of the elastic modulus or the shear modulus, there's really not much going on. The density also is also changing quite a little. You hardly have any changes in the valence electron concentration, because the valence electron concentration of all of these elements are more or less the same. And then if you look at the asymmetry in covalent radius, that again you will see that there is a change, but there's not a whole lot of change. So from this type of analysis, you can see that it's really one of the features which is changing significantly, and it is really that feature which is contributing the highest to the hardness value. The asymmetry in covalent radius is changing, not as drastically as the delta H chem, but it is changing in a much more gradual manner, and therefore it also has an influence, but not quite as much. One of the things you will also notice is when we are talking about the feature values, we are talking about the normalized feature values, and that is important just to ensure that when we are talking about changes in the feature values, we are talking only about the changes relative to its own starting value. Doing that is actually quite important, because that ensures that no particular features gets undue bias or undue weightage. So there you have it. In a nutshell, we have talked about a couple of different research papers where the machine learning models have been interrogated using a couple of different techniques. And prior to that, we have talked about how you can start setting up machine learning models. So hopefully by end of this lecture, you now have an idea of what has to be done in order to put together a machine learning model, interrogate it, and then start extracting physical insights from it. So with that, we are going to stop here for today. And then as we move forward tomorrow, we will talk about physics-informed machine learning, which is a little different from extracting the physical insights from this black box type of machine learning models. Thank you very much for joining with us. See you again tomorrow for the next lecture.